On the hottest afternoon of the year, walk into a basement and notice what happens. The upstairs bedrooms may feel unbearable. The attic may be holding enough heat to make the ceiling warm. Outside, the pavement may be too hot to touch, but below ground, the air is noticeably cooler. That temperature difference is not coming from an air conditioner. It is coming from the earth surrounding the foundation. And with the right design, that naturally cooler environment can help reduce the temperature inside a house before a compressor ever turns on. This is not a replacement for air conditioning in every climate, and it is not a magic pipe that will cool an entire home for free. But it is a real form of passive cooling that has been used in different forms for centuries. The concept is usually called an earth tube, ground-coupled ventilation system, or earth-to-air heat exchanger. Despite the complicated names, the basic idea is simple. Outdoor air enters one end of a buried pipe. As it travels through the pipe, heat moves from the warmer air into the cooler soil surrounding it. The tempered air then enters the building. Think of what happens when you place a warm drink inside a cool refrigerator. The refrigerator does not instantly freeze the drink. It gradually pulls heat away from it. An earth tube works through a similar exchange, except the surrounding soil acts as the cooler environment. A few feet below the surface, soil temperatures are much steadier than the air above them. The exact temperature depends on the region, soil, moisture, depth, and time of year, but the ground is protected from the rapid temperature swings happening at the surface. A summer afternoon might reach 100 degrees, while the deeper soil remains far cooler. That creates an opportunity. Instead of pulling blazing outdoor air directly through an open window, a properly designed system gives that air time to lose some of its heat before it enters the house. The longer the underground path, the greater the surface area available for heat exchange. Pipe diameter, airflow speed, soil conditions, depth, and installation quality all affect the result. That means the system cannot be reduced to one universal measurement. A short pipe buried too close to the surface may do very little. A longer system installed at an appropriate depth in suitable soil can create a much more noticeable difference. But cooling the incoming air is only half of the equation. The hot air already inside the building needs somewhere to go. Warm air naturally rises. When a high window, roof vent, cupola, or properly positioned exhaust fan allows that hot air to escape, lower pressure air can be drawn in from below. This creates a continuous pattern. Cooler air enters low, warmer air rises, hot air exits high. The building begins moving air in the same direction that heat naturally wants to travel. Long before residential air conditioning became common, builders used versions of this approach without calling it an engineered cooling system. Homes were constructed with tall ceilings so heat could collect above the occupants. Transom windows allowed air to move between rooms. Covered porches reduced direct sunlight. High openings released trapped heat, while cellars and shaded lower spaces remained cooler. These buildings were not perfectly comfortable by modern standards, but many were designed to manage heat instead of sealing it inside and depending entirely on mechanical equipment to remove it. Modern homes often take the opposite approach. They are tightly enclosed, heavily insulated, and organized around central heating and cooling. That can be extremely effective, but it also means the house may have few ways to release accumulated heat when the air conditioner is off. Passive cooling does not require abandoning modern equipment. It can work alongside it. Every degree of heat removed naturally is heat the compressor may not need to remove later. Before anyone considers digging a trench, however, the easiest place to begin is with the structure that already exists. A basement is a good example. During summer, basement air is often cooler than air on the upper floors because much of the space is surrounded by soil. Homeowners frequently leave that cooler air isolated downstairs, while the air conditioner struggles to cool bedrooms above it. A fan placed near the bottom of an open stairway may help move cooler air upward. At the same time, opening a carefully selected window on an upper level or using an exhaust fan can provide an escape route for warmer air. The goal is not simply to point several fans into random rooms. The goal is to create a path. Air enters from the coolest available location, travels through the occupied area, and leaves from a warmer, higher location. The direction matters. If every window is open without a plan, air may take the shortest route and completely bypass the hottest parts of the house. A more deliberate setup can work better. Identify the coolest lower area. Move that air toward the living space. Open an exhaust point on the warm side or upper level. Keep doors open along the intended airflow path. Block unnecessary openings that cause the air to take shortcuts. This basic arrangement costs little to test and does not require changing the structure of the house. A buried earth tube is a much larger project. A typical concept uses smooth, durable pipe installed underground with an outdoor intake and an indoor outlet. The intake needs protection from animals, insects, leaves, and rain. The pipe needs to be positioned so water does not remain trapped inside it. That last point is critical. Whenever warm, humid air passes through a cooler pipe, condensation may form. If water collects inside an inaccessible underground tube, it can create odor, mold, and air quality problems. For that reason, an earth tube should not be treated like an ordinary piece of drainage pipe thrown into a trench. Drainage, clean-out access, pipe material, slope, filtration, soil gases, local humidity, and maintenance all need to be considered. In some locations, radon is another concern. Drawing air through or near the soil without the proper design could introduce contaminants rather than improve the indoor environment. Local building requirements also vary. Underground utilities must be identified before digging, and a homeowner should contact the local utility marking service and building department before beginning any excavation. A well-designed system manages those risks. A careless system can turn an interesting cooling idea into a damp underground air duct that nobody wants connected to the house. There is also an important difference between ventilation and air conditioning. An air conditioner does two major jobs. It lowers the temperature and removes humidity. An earth tube may lower the temperature of incoming air, but its performance with moisture depends heavily on the climate and design. In a hot, humid region, bringing in large amounts of outdoor air can increase the moisture load inside the house. In a hot, dry region, the same approach may be far more useful. That is why results vary so widely. Climate matters, soil matters, depth matters, pipe length matters, airspeed matters, the home itself matters. The most realistic way to think about passive ground cooling is not as an appliance replacement, but as one part of a larger heat management strategy. Shade the windows receiving the strongest afternoon sun. Ventilate the attic. Seal unwanted air leaks. Use exterior shading where possible. Run heat-producing appliances during cooler hours. Move cooler nighttime air through the house. Use the stable temperature of a basement, crawl space, or underground system when it can be done safely. Together, these changes can reduce how quickly a house heats up and how hard the cooling system must work. A buried pipe gets attention because it sounds unusual, but the bigger lesson is about controlling heat before it becomes an indoor problem. Once sunlight passes through a window and heats a floor, wall, or piece of furniture, that energy is already inside. The air conditioner must then collect the heat and move it outdoors. Stopping the sunlight with exterior shade is easier. Once attic temperatures climb, that heat begins transferring toward the rooms below. Venting and insulating the attic reduces the amount that reaches the living space. Once hot outdoor air pours directly through an open window, the cooling equipment must deal with it. Tempering that air first, or waiting until nighttime to ventilate, reduces the load. Mechanical cooling attacks heat after it arrives. Passive design tries to prevent, release, or redirect it first. That distinction was once a normal part of building a home. Today, many houses are designed under the assumption that the heating and cooling equipment will compensate for everything else. Poor orientation? Install a larger unit. Unshaded western windows? Install a larger unit. Heat trapped upstairs? Install a larger unit. An oversized system may lower the temperature quickly, but it does not always solve comfort, airflow, or humidity problems efficiently. Sometimes the first question should not be, how much more cooling equipment does this house need? It should be, where is the heat entering? Where is it collecting? And where can it escape? You can begin answering that without buying anything. On a hot afternoon, walk through the house with a basic thermometer. Check the basement. Check the lowest occupied floor. Check the upstairs hallway. Check the room facing west. Check the attic entrance. Check shaded and unshaded rooms. The temperature pattern will often reveal the real problem. One room may be overheating because of a large sun-facing window. Another may have poor airflow because the door stays closed. The entire upper floor may be holding hot air with no exhaust path. Once you see the pattern, the solution becomes more specific. Some houses may benefit from moving basement air upward. Some may need exterior window shades. Some may need better attic ventilation or insulation. Some properties may be suitable for a professionally designed ground-coupled ventilation system. Others may not be suitable for an earth tube at all. That does not make the principle useless. It makes it a tool rather than a miracle. The ground beneath a home contains a stable thermal resource. Whether that resource can be used effectively depends on the building, climate, and installation. The most valuable part of the idea is not that a pipe can supposedly eliminate your electric bill. It is the realization that cooling does not always have to begin with a compressor. Sometimes it begins with shade. Sometimes it begins with airflow. Sometimes it begins with releasing trapped heat. And sometimes it begins a few feet underground, where the temperature changes much more slowly than the summer air above it. Before spending thousands of dollars replacing cooling equipment, study how heat moves through the house you already have. You may still need the air conditioner, but you may be able to make its job considerably easier.